FST, easy as 1, 2, 3. Okay. 10.2 and 10.3. Mean and standard deviation of binomial distributions in fair coins. That sounds like a mouthful. And they seem kind of unrelated, but they're not really. Mean and standard deviation are terms we've done before. Mean is just as you've expected it to be. It's the average of a list of numbers. Mean in binomial distributions now is going to be like on that. Here we go. That what am I trying to say? The multiple choice thing from example from last class. Go away. Is that we had 6 questions and each one of them had a 20% chance of success. What was the mode of that? Like, what's the most popular score you get on the test if you're just guessing? This is more about, okay, what's the average score you should expect to get? And lo and behold, that actually turns out quite easy to calculate. Oh, I always do this. Before I get to that, here's your questions for the do now when I first see you. Sorry, it's not quite fitting in the window. For the do now when I first see you after you've seen this video, and this is the kind of thing you're going to do. If you had a test with 14 multiple choice questions and you guess what's the mean number of questions you should get correct. Before this, we would give the distribution, like the 10-1 stuff. You'd give the distribution and you should show like what's the mode kind of test score you'd receive and how the other test scores that are possible would compare to that. Now we're actually talking about what's the actual average. Okay, anyway, this one is about mean. So yeah, 1.2 out of 6, which guess what is actually just 20% of 6. All you have to do for this one is calculate the number of trials times the probability. So if you had 10 questions, you had 10 true-false questions. I guess that one's kind of a little oversimplified, but let me finish that one. If you had 10 true-false questions, you just take 50%, which is your probability of getting it right, of 10. And you should get an average of 5 right. That one's kind of an oversimplified version. Say you have like the thing with the bulbs. Let me draw this for you. Say there's 15 questions on the test. So you think you have an 80% chance of guessing any one question. What's the mean expected score you should probably get on this test? Well, guess what? It is actually 15 times 0.8. They go to a lot of trouble in the book to tell you that that's what that is. And that's actually just 12, but it's exactly probably what you would expect. No big surprises there. Okay, there you go. All right, the other thing about this section is about standard deviation. Now, I know it's been a while since we've talked about standard deviation. Standard deviation is about basically how spread apart things are. We did this way back, I think, in the middle of first semester when we were talking about the heights of people on a basketball team, and there was the average height, then you had some taller people and some shorter people, and the standard deviation measured it's kind of like saying how far is the average person away from that average. It's calculated by this big crazy sigma thing. You take each term and you subtract the average from it, so you find out how far is it away from average. You square that basically to make it positive. Find the average of those added up, and then take the square root to take it back down to not being a squared number anymore. Before you square root it, though, it's called the variance, and if you remember from first semester, variance was really not that valuable of a statistic. We really cared more about standard deviation. And you're probably going, oh my gosh, we're actually going to find these standard deviations for things in binomial distributions, and there's so many numbers going on at once, I don't even know what to do. Well, it's not that bad. All you have to know for now, and we really aren't, computing with those very much right now. You're just kind of learning out how to figure them out. The standard deviation of a binomial distribution of n trials and probability p success, and they have to put q in here too. Is there an extra space there? It kind of looks like there is. Nope. Okay. Is that you just take the square root of those 3 things being multiplied together. So let's go back to the example we were just on. What's the standard deviation of all that? Oh, by the way, we call this mu. And standard deviation we would call sigma, little sigma. You take npq and take the square root. This would be n. This would be p. And the thing about q is, I kind of wish they wouldn't say q. They would just say 1 minus p. Q is like the chance of failure. So in this situation, q is actually 20%. And why we have to multiply those 2 things together times this is not something I'm going to make you reconstruct. I should change to answer mode. 15, well, this is like the mean in here, isn't it? 15 times 0.8. But I also have to take that times 0.2. it kind of looks like part of the binomial expansion. This is 12 times 0.2, which is our good friend 1. Oh, wait a minute. 12 times 0.2 is 24. I thought it was a different number. 2.4. Take the square root of 2.4. That is not a nice number. It's about 1.55. So that kind of means on average, now we're not going to get really into the interpretation today, but that kind of means that on average, these other scores, because the scores you could get would be anywhere from 0 correct to 15 correct. We would expect on average you'd get 12. I didn't compute the mode today. We did that last time, so I'm not going to do that. But standard deviation is more related to mean anyway. The mean is 12, and that kind of means that most of the numbers are spread out with a standard deviation of 1.55. So there's a lot of numbers that are, you can kind of expect them to be kind of typically 1.5 bigger or smaller than this. Now that's not a really good way to present standard deviation, but the bigger the standard deviation, the more spread out the numbers are. If the standard deviation is really small, then they're all really clumped around 12. That's kind of how that works. All right, I'm looking at the worksheet now for 10.2, and I'm thinking you'll be able to do everything on there. What's interesting about this is that by the time you get to number 6 on the 10.2 worksheet, it says, suppose you flip a quarter 16 times and count the times it lands heads up. What's the expected number of heads? You can probably do that in your head. But then the next question is, what's the probability that the number of heads is no more than 1 standard deviation away from the expected number? And this is a great segue into 10.3. 10.3 is about binomial experiments and deciding, how you look at the results of one and you go, okay, how crazy were these results? Is this something that's supposed to happen? Is this experiment or is this situation truly random? And did it fall within the realm of likely probabilities, or is there something else at play here that I'm really not considering or not calculating correctly? So it's about kind of judging the reasonableness of results, which is a really good skill for any well-functioning adult to be able to do. So you talk about, we've talked lately in FST about how sometimes this stuff doesn't apply to real life, but as we near election season, this kind of stuff is great. We're talking about fairness. We're talking about whether or not things are turning out the way they seem, or if there's something else weird going on. Because you're about to get bombarded with things in the media about poll numbers coming back, about candidates and confidence levels and all this kind of stuff. Anyway, I should get back to the task. All right, just getting excited about real life every once in a while. Okay, so they use the coin example in this. Well, the coin is actually the title of the section, but a coin is a perfect example of let's test for probability. I'm trying to get that thing to go away. I can't get to do it. Let's test our probabilities and see if the coin turned out the way it was supposed to, or is it so weird that I can sort of accuse this coin of being unfair and mathematically prove that there's something going on here that's not supposed to be going on. So the one they do in the book is they've got this coin that comes up 39 times heads. They think that's not really cool because it should be more than that. So let's come up with this hypothesis that, now wait a minute, 39 is kind of weird. 39 or fewer, how often does that even happen? Here's how you test for this. You go, how weird is it that I get 39 or 38 or 37 or anything weirder than that? And let's see how often that actually happens. Because anyway, that's just how they do it. The hypothesis here is either, we talk about hypothesis later, is that either the coin is fair or it's not. If it's not fair, then we should lump this in with anything that happens more extreme with it also, and see if this is a significant enough probability kind of mistake. So what they do is they calculate that all really quickly. They say 39 or fewer heads out of 100 tosses, about 2%. And you kind of go, whoa, how'd they do that? Well, they do write out a sigma notation version of it. Here's the way we would do it on our calculator. You can do it in 2 lines on your calculator, and you get this number that's actually better than the number that's in the book, just to make you feel better. You can put this in. The binomial probability distribution function, I think is what that means, of 100 trials, we're tossing the coin 100 times. The probability of success is 50% on each one of those. We're going to store that as L2. And then we're going to add up a whole bunch of L2. We're going to add up the first 40 from L2, the first element, to the 40th element. That would be from getting 0 successes at the first element to getting 39 successes at the 40th element in that list. Add up all those 40 probabilities, and it's still like less than 1%. So that is pretty crazy. They double this, and this is a little bit confusing, I think. Why they have to double this when they're talking about all the outcomes that are just as crazy as 39 or fewer heads. Well, they're saying 39 or fewer heads is just as crazy as 39 or fewer tails. So basically, the coin not being fair has to do with how often it's coming up the same way, and it's not coming up randomly both. So if we double that, we talk about how that's then it's going to be almost 4% of the time. Actually, it's closer to 3.5. 3.5% of the time, this book decides, and it's sort of a common thing. If that's an outcome that could have happened up to 4% of the time, that's really not that weird. It depends where you draw your line. If 4% is okay with you. Many times I draw the line at 5%. So if 5% is sort of your tolerance for fairness, then this wouldn't be fair. But a lot of the experiments you're going to see in this book, they use 5% as the cutoff. Sometimes it's 1% or even 1/10%, depending on how fair or not fair you're going to allow something to be. That tolerance line is called the significance level. You kind of get used to this language after a while. You say you reject a hypothesis at the 0.05 significance level, means the event consisting of the experiment's outcome and all more extreme ones has a theoretical probability that is less than 5%. Okay, so yeah, that's the tricky part, is getting all the more extreme ones lumped in there also, and you have to add those all together. It's not just the probability that 39 heads happened, because that's pretty rare. That it would be exactly 39, like, it's not going to happen to be exactly 39 very often, and that's okay, and that's not weird. What's weird is how often is it 39 or anything more extreme than that? How often does it get to be at least as extreme as 39? That's kind of what we are concerned with. And it only gets to be that extreme and anything more extreme all lumped together something like 4% of the time. All right, so then there's this discussion of what's the null hypothesis, what's the alternative hypothesis. Null hypothesis is basically the hypothesis that there are no outside forces acting on your coin or your die or your political candidate, or, null hypothesis in politics would be something like that all the candidates have an equal chance of winning. Alternative hypothesis is that usually there's some bias going on, like this coin is weighted towards the tails side, or this die is going to turn up 3 more often than anything else, or it never turns up 4, or that one of the candidates is actually better than someone else. So they use these statistic measures and these significance levels to make decisions about how great the campaign's going. All right, so here's an actual problem. I'm going to toss a die 40 times, and it comes up 15 of those 40. How crazy is that? That's kind of like the question we're going to answer, but the way we're going to frame it is it fair to the 0.01, to the 1% significance level? Okay, so first of all, I have to add up all the probability that this thing's going to come up 3 that much. Well, for that, I need the distribution of the tossing of a coin 40 times. First of all, the probability of success here that's going to come up at 3 is 1 out of 6. And the calculator will not accept fractions, which is a pain. Will not accept fractions for the success probability, so you got to enter it that way. Okay, so I'm just going to talk you through this. Cleared all my lists, so I'm starting from scratch here. All right, I want to calculate the distribution. Jump to A. Is that the right one? Yes. 40 trials. Success rate 0.16666, blah, 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 blah. Okay, so, and I'm going to store that. I'm partial to list 2 these days, in case I ever want to graph it. I'm just getting the habit of storing stuff under list 2. So there's the probability that I never roll a 3. Here's 1 3, here's 2 3s, here's 3 3s. Now the hypothesis I'm testing here is that I think this thing is unfair because it's too many 3s. So I really want to know what's the probability of getting 15 or more 3s. Like, how often does that happen? That's the crazy end I care about here is, wow, that seems kind of high. If I count the probability for 3 or fewer, well, that's going to happen a lot. I'm going to expect to get like a 1/6 of these to turn up 3s, so that's not weird. What's weird about this is this seems too high. So I'm going to say, what's the probability that I would get 15 or any more than that in my 40 rolls turning up 3, because that seems pretty crazy. So now that I've got that list stored for L2, I'm going to add up a bunch of it. I don't want to add... I want to add up from 15 successes on down. Now, if this is row 1, that's the 0th success. So I have to actually start my sum at the 16th one, which would be list, find the sum of L2s. I want to start at the 16th one, and I want to go to the end, which is the 41st one, because there's 41 things in that list. When I add those up, I get about 1%. There's about a 1, if I add up all these past a certain point, see, that's 16% right there. Add those all up, I only get 1%. Sorry, 0.1%. So this is way too crazy. This is not supposed to happen that often. This thing fails the test. If it were truly random, it would only happen that much time, not nearly close to this much. All right, I'm out of time. See you in class.